For
Yep.
when is it called?
I think this semester every 2 years or something.
Okay, let's get going.
I don't know. I'd rather take it.
So first thing, so how's the homework? Did everyone submit?
Like halfway.
Halfway?
Almost three.
Well, there is no other.
I did it, but it keeps failing tests. Like.
Talk to Jerry. That's cool. Okay, so, but okay, let's try to submit tonight, right? Tonight is the deadline, but if you, like as usual, no huge penalty, but we should start working on the next one. And I mean, we started talking about context switch, but I realized that I kind of lost you guys. And I really wanted I want to step back and take it slow and make sure that everyone understands what's going on there. So let's just start with a very simple example, which is this, but we will first ask it differently. So what is that? It's my final exam from the version of this class, but from UC Irvine. So essentially, okay, the questions go like this. Essentially, I assume that people know how context switching works, right? Because I taught it in class. And I asked the question, the following. So Ben decides to implement user-level threads. His plan is to create a new thread data structure that describes the thread. He then thinks he can allocate a new stack for each thread and implement function uThreadCreate. U stands for user, right? Which creates a new thread. The uThreadCreate has the following signature. And I say it's exactly the same as something in a homework assignment. So essentially it takes a pointer to the thread data structure, pointer to the void function, pointer to the void arguments for the function, and pointer to the stack, right? So that's a reasonable kind of like setup to create a thread, right, of execution, which starts executing from this function with those arguments, which are passed to this function and on this stack, right? The uThreadCreate then creates a new user thread that runs inside the same process, in contrast to the kernel thread implementation like in x86. The uThreadCreate doesn't evoke a single system call, but instead just executes the function that it's passed as an argument, fn, the already allocated stack. It's the same. What's important here is this. The new thread then runs until it explicitly yields execution back to the parent with the yield call. The yield, u_yield, doesn't do a single system call, but saves execution of the thread on the stack and switches back to the parent process. In other words, it continues execution at the line immediately following the uThreadCreate invocation. Ben then can create and run multiple user threads like in this example. So take a look at the example. So it's all user level code, right? And just to make sure that we are, here's the code for you. Jesus, I have to, this I have to hide from you guys. The solution I will hide. But like user level threads, do we understand the idea? Do you understand how it works? So let me explain it by example. You have a main function here. You have two stacks. You have two. Okay, you allocate two stacks, line 97, 98. You say, look, I will use those functions uThreadCreate, and I will pass them pointer to the thread data structure and some word function with some argument, and I'm passing this string inside, right? And one executes on stack one executes on stack two. And then I run a loop and I say, look, if the thread is if either of the threads is in a runnable state, I will continue running the loop. If thread one is in runnable state, I will yield to that thread. We'll run the thread for a little bit, right? So it kind of logically looks like there was this thread in which main was running, then I yield, let's say T1. T1 runs and then yields back. We'll see in a second. So everything is cooperative, so no timer, nothing, right? The main runs, then I yield to T2, and then T2 yields back to main, right? And if I show you this do work function, which I'm calling here, it's very simple. It's just essentially runs the loop for some number of iterations that this print sign in the thread which was passed as an argument, and then yields back the parent, right? And if we compile and run this, I needed a, it's too hard to compile on Mac, so I just make clean up, make fast. So it essentially shows you this on the screen, right? So, and if we follow the example carefully, we see that those functions, they literally, I'm in thread 1, then it yields back to the parent, then it yields back to thread 2, I'm in thread 2, and so on and so on. So this is essentially context switching, but written as a user level C program, right? Make sense? And I mean, if you're in a language community, you say, look, guys, I kind of got it. So it's very similar to something like async, where depends on what you want to do. You can say, I will execute a function foo and a function bar, and immediately they are in the loop. You can say for I in something, execute, I don't know, like let's imagine something like IP lookup of a specific, like you have array of names, right? And you say, look, the idea here is the following, that when you write something like this in a language, you say for some I in some range, I'll be doing an IP lookup, but if IP lookup somewhere deep inside, when it sends out the DNS request lookup logs, it continues execution from the next line here. Probably it's better to write and essentially like does the next iteration of a loop. So essentially it just like sends out a bunch of DNS lookups, and here at this race, it just waits for all the threads to actually converge, right? And I'll show you how to write it even in C with the help of macros in C, like kind of funny, right? But it still works, right? And my example does kind of exactly the same, right? So it's less sophisticated, and I really just write something like you see what it's right. You get the example? Do you agree that it's context switching and it's not too far from what I want to build in a program? There is no timer, everything is cooperative. But the moment you understand how this works, you will understand how to build it with a timer. Agree? Okay, now, because I forget what exactly I was asking on the exam, but probably like roughly the same thing. So now tell me how to build this. What should be inside this yield to function? Or maybe inside thread create and everything.
Is this purely user space that we're talking about?
Yes. No system calls, nothing. And I like I'm saying in this in the question.
I think I have a big idea.
Yeah, sure.
Each thread is a state machine where it can enter at different points. So anytime you call yield, it needs to record the following address so that it can enter there. So when you're passing T1, it would have to be a struct that has the program counter inside of do work, as well as all the the stack of do work. And so yield to is just, I guess, a dynamic to the program counter after setting RSP to the stack.
At a high level, agree. I mean, you mentioned that state machine, not exactly. But I mean, maybe just to simplify the thing. I mean, and you said dynamic go to, just let's assume I will be using assembly. So I think you captured the essence of what needs to happen, right? So you say, look, I was in main and I tried to build a yield function, which says, okay, it will take a pointer to the data structure T. And you say, look, I should start executing from some point in T, right? And you can say, look, at the very initial state, the T at least needs to have 2 pointers to the stack, which is empty, or maybe can contain like some arguments here, because like this code actually was, because I was teaching 32-bit version of the class, it assumes that the argument is passed on the 32-bit convention is to pass the first argument on the stack. And so there will be a pointer with to the stack with some argument passed, and will be a pointer to some label inside T1, and of course initial label, since we created T1 by passing this work function, right? So it will be probably to do work, right? So at least you say, look, like you mentioned dynamic go-to, but in assembly it can be something like a jump, right, to a specific address which will pass as part of this, right? Somewhere, I don't know, like I don't want to use a register, but let's say we know that it's new work, right? And so if we're writing this, if we have this yield function, right? And maybe we will write a like lower level switch function, which I don't know, like some of it can be written in C, right? So then you say, look, I entered yield with this argument T1, and I like you want to do something like T IP counter right here, although it will be encoded in assembly likely, right? I will pass like probably will be in a register, right? Roughly speaking, this is what it means, right? And we say, look, if I move into my stack pointer ESP register, I will move something like T stack pointer, then I will achieve this diagram, right? Agree with this? This piece of assembly, which just says, okay, I'll jump to TIP, right? Make sense? And do work starts running, right? At some point, do work says, I mean, I want to yield back to, let's call it the parent. This yield to parent, right? And so we want to come back to this thread, which called yield here, right? So how do we do this? Maybe stop sharing to make sure that the screen is recorded.
You save the stack and the program counter in the same structure, and then you jump to I suppose it would need to have an additional address in the structure for where you jump back to an original SP. So you're just swapping SP and IP with the one from the parent.
Okay, I agree with this. So if you have a parent, right, you say, and I want to come back, so I want to return. Wow, maybe I don't care. Maybe I just want to return from this switch, right? It's a little simpler, honestly.
Should we have a separate stack for storing the parent address?
Yeah, there was some stack, right? I agree with this, right? Agree? And maybe we created a heap structure. Which I don't know where it points, what state it has, but if we pass it here as an argument, if we have two arguments to yield, or maybe some lower level yield, like two arguments from and to, this p is passed inside, so it's known here as at some point maybe switch takes two arguments like from to, right? And you say I will write to ESP, and we somehow like don't want to be very specific, but like just to EAP, right? So we're gonna jump to this too. We want to save. Talia was saying that we want to save the state of from, right? And Talia says, okay, we want to save two things: ESP and instruction pointer, right? If we think for a second, what's the easy way to do this? How to save this to? And there are multiple ways to do it, so there is not like a single way. Just let's suggest at least one. On a stack? Yeah, I agree. In fact, what about instruction pointer? Maybe it's already switched, or maybe it's already saved on a stack. If we just use a regular call instruction to invoke switch, so instruction pointer is already sitting on this stack, right? And again, I will show you different ways, but we know the convention. When you do a call instruction on 64 or 32-bit x86, it will save return address on the stack, right? Remember this? Okay, so instruction pointer is saved. So you really just need to save ESP, right? And sure, you can say, I'll just do something like from ESP, just save my value of the ESP register. Make sense?
And then you just do a regular ret, then you're back into the parents.
Right. So then you say, look, if I adopt this convention that instruction pointer is saved on a stack, then I can also kind of like when I yield to this thing, I can assume that my stack has a return address, and in the very, very beginning, it will be returned to do work. So when we do this create thread function, we will put do work, the initial label, which we pass here as a return address on this step, right? Right? And then my stack will be something like this. A return label, and then the argument, which is one above, right?
I was thinking something different, because if you put it on the thread stack, then that means you need to top all of the thread state if it wants to return back. I was thinking you put the return address on the parent stack, because for the parent to switch to the thread stack in the yield to function, it's already going to pass it's going to push the return address at that call site. So then you get it for free. You switch back to the parent stack and then return while on the parent stack, and then you're back.
You lost me a little bit, but I kind of argue that this is the simplest way, and then we can discuss deviations, which may be a little bit more elegant. But okay, hold on. I just want to make sure that everyone understands how it works, right? Like, ask me a question at this point, something is unclear.
That's where I thought as well that we store the return address on the parents.
On this parent stack,
Yes.
like, bear with me for a sec. Let's put it here. It's just easier.
Well,
Although
how do you have local state in this?
I'll show you in a second. Right? But if we, instead of this jump, we'll do a regular ret here, right? That should work, right? So what I'm doing here, when I'm entering this low-level switch function somewhere inside yield, my return address is already pushed on the stack as part of this switch invocation, right? So I just, from this P, what is it called? ESP field, I'll just set it to point to this stack. And if I'm passing T as an argument, and T points T's ESP field points to a well-formed stack, I can simply return and start executing inside T1, right? Is it too much or?
I think we might be saying the same.
Yeah. But no, I'll let everyone else understand what's going on. Wait, do you agree that this is a context switch? So I module at the registers, which Talia says, okay, where is the state, right? Module at the registers. Imagine for whatever reasons we figured out how to save and restore registers for a second. It's very simple. We'll figure it out in 2 more seconds. We agreed that these 2 lines implement the context switch by simply switching the stacks and assuming that at the top of the stack, there will be return label, which allows you to return back to the thread, which later on to the thread to which you're yielding. So you saved when you do the call instruction, you save the return address for the wrong thread, and here you're returning to the true thread. Here you save EAP for the from. Make sense? Yes or not? Okay, do we buy that it works? Okay. Okay, cool. Now what about the state? So Talia says, okay, look, like clearly, if I'm running this loop in some kind of like iteration, and I called yield here in my 97, I have my register states, like state to be specific with this variable I. It's probably allocated, despite the fact that it's a local variable, compiler is smart, so it's not going to push it on the stack, so it will be in a register, right? And obviously, the next iteration, when I yield away to the parent, we did this loop, parent yields back to thread 2 or 1, and we need this state of this variable I. How can we save and restore it? Alia knows the answer, but someone else. Jerry, are you awake?
Yeah.
You're not awake. How do we save registers? Like, how do we save the value of this variable I inside this switch function? What are you saying? Push it onto the stack. So how do we push it onto the stack? No, I get it. It was a push instruction, okay, but or move instruction. But let me know, like what is that we need to push? We don't really know where I is. Can we here, for example, push all registers?
Just everything, all the general purpose, all the AVX, all the weird ones.
We'll get to that in a
Make it
second.
slow.
No, slowly. You see, I'll help you in a second. But if I push here, and if I say restore here, does it work for you guys or not? Why it should work, right? I'm saying I'm pushing all registers, and like they get pushed here, right, on this stack, for example, 1 by 1, right? And I obviously my ESP will be pointing to the very top of this stack. So the next time I come back, I'll do the opposite code. Like if I wrote here something like push EAX, then I will do pop EAX and then return, right? And so here I saved it when I said this line push all the registers. I push EAX, which means that EAX is saved on the state on a stack. And then I pulped it, so which means that if I have a value of EAX here on this stack, at the very top of this stack, sorry, the other way, right? So it's EX will be here, whatever the register you choose. Since they don't have a numbers, I don't know. ESI, I don't know, something like this. The very last before I do this will be push, let's say ESI. Then we do this two move instructions to switch the stack, and then obviously here the very first one will be pull ESI. Agree?
So I think it needs to be symmetric, as in
Yeah.
you push the parents' registers, you switch to the child stack, you pop the child's register.
Correct.
Then to switch back, you push the child register, switch to the parent stack, pop the parent register.
Yeah, exactly, right. So here we're saving everything from the from thread, and here we're restoring everything from the to thread, right? And everything is, just for this second, imagine, is saved here. This will be saved from, and this will be already saved previously on the to stack, right? So agree? That will give us saved state, right? Very blindly. Hold on again, wanted to make sure that everyone understands, because it's just literally impossible to make it simpler in terms of explanation, right? So if you saved all the registers here, they're saved here either with a previous context switch, or when we were creating a new thread, we'll just make sure that this stack is set up correctly with zeros, for example, right? And we get going there. Make sense? So now, when you're calling a function, like, imagine we did this call, yield, and switch. And switch takes two arguments, from and to. And imagine, just for the sake of concrete example, that this is 32-bit assembly or 32-bit machine code, and the whatever it's called, system 5. Is it the same system 5 that we're digging? So they are the two registers, the two arguments. The ABI is that they are pushed on the stack. So from will be the closest. This will be a return address. From will be the closest, and to will be one step away on the stack, right? Stack is going downwards, right? Right? This is exactly what I'm doing here. Yield and switch, right? With two arguments. What's the C calling convention? The system 5 calling convention. What's the obligation on this function? Which registers this function is supposed to save? Is required to save? Dominic should know the answer. He's a compiler person.
I hate conventions.
I hate them too. And I don't remember them, but at least I keep it.
I just look it up every time.
Me too. Like, do you think I remember it? But at least we know what are those two magic words which we have to remember. Yeah, caller saved registers and callee saved registers, right? So, I mean, it varies from convention to convention. That's why none of us remembers it. But there is two set of registers. Roughly, you can imagine the register file, this all registers are split in half. And callee, the switch function internally, if it uses some, there are two sets of registers. One is callee saved. That's the callee has to save and restore them on the return, right? Or caller save, which means that the callee can use those and don't even bother to save them, right? So obviously in our switch function, which registers do we have to save? The other way, inside the switch. Oh, it's callee, right? Because if yield function cares about the register from a caller set of caller saved registers, it will push it here and will pop it here themselves, right? We don't have to care, right? Or just like whatever, the value is not important, right? So that's why instead of saving all the registers, we're only saving the Coley saved registers, right? Make sense? So it's a much like when Talia says, okay, we save all, everything becomes slow. I say, look, it's really not. Like on 32-bit machine, there are only 8 general registers, and roughly half of them are Coley saved, even less probably. Right? So you're only saving like 5 registers.
So when you're switching from parent to child, you're saving color saved, and from child to parent, you're saving Coley saved.
No, you always say saving only Coley saved. Why is that? Because we're calling a switch function, and for the caller, it looks like a regular function. The caller doesn't know that something magical happened and we switched away. Caller thinks, okay, I switched, and return, it saved all my Coley saved registers, returned back, right? So we're only saving always Coley saved. So these are Coley saved. And we restore Coley saved. Right? Make sense? Agree with this? So sure, then if we do this trick, then I kind of argue that this context switch is complete, right? We like calling convention doesn't cover ESP register, so we handle it. Well, we handle it in a tricky business. We just replace ESP, so we do really save it inside this thread data structure. And calling convention doesn't really like talk about instruction pointer because okay, they assume that it's saved on the stack and restored with a ret instruction. But okay, we'll also carefully handle it because we don't do anything with it on the stack, right? Makes sense? So okay, let's take a look at how it's actually built. So not exactly sure why I built it this way. So that's modular aside my implementation. So there's probably a better way to build it. But here I say yield2 has a thread. It saves it in a global variable current, uses a low-level underscore switch, use switch function, where it passes a pointer to the parent, which is my main thread, which I maintain somehow in a program, right? And pointer to this to-thread, right? This uSwitch. uSwitch itself is implemented as this low-level assembly function. Again, there is no explicit make keyword here. So technically speaking, this code is incorrect because who knows, maybe compiler will insert something. Here, like, I mean, you guys should tell me how to write it properly. Probably have an assembly routine and linking it for simplicity. And based on the expertise that GPT never really does it, it worked. But really what it does here is that it has a global label with switch. 2 arguments are passed on the stack, right? As I said, calling convention, the to and from are passed on the stack. I'm using 2 of the caller saved registers. I mean, according to the calling convention, if caller needs them, they have to save EAX, right? And they have to save ECX. Okay, sure, I say it's a GCC syntax for whatever reason. It was maybe more, it was easier, GCC compiler. So I'm saving from the stack to the EAX register, saving from the stack plus 8 into the ECX register. Those are my from and 2 threads, right? Then I'm pushing those, there are only 3, turns out to be fully saved registers. EBX to the ISI, EBP, also fully saved actually. What am I doing here? Explicitly saying EBP on the thread data structure. Why? Not exactly sure. Just what's important, I don't know why I'm not pushing EBP onto the stack. Maybe just something within my head. But really, what's important that I'm just saving the stack into the from data structure plus 4. So it's in the data structures probably has like several fields. And let me just I don't know where it is. Yeah, here. So it has EBP, SP, and obviously they're like I use the same alignment. So ESP is plus 4, right? Make sense? Agree with me? Then I'm flipping the stacks. Here. Okay, so I'm again using like, so ECX contains two thread data structures. So I'm restoring EVP, restoring ESP, restoring 3 other equally safe registers, and returning. Right. And again, like the only awkwardness in this code, I don't know exactly why I did it this way. I would say it's cleaner to push this to treat EBP as a regular wholly safe register, and we clearly have 8 registers split by half. So it's like 4 wholly safe registers. Make sense? And then it runs. So essentially what I'm doing here, when I do a thread create, I say, remember, when I create a new thread to which I never context switched before, I have to set up a stack in such a format that when I enter the switch later on, it can restore the registers, right? And jump to the do work function. So this is what I'm doing here. I say state of this thread is runnable. I allocate the stack. Stack was allocated. I just jump from the beginning of the stack to the end of it because the stack goes backwards, right, in memory. And then I'm saying, okay, sure, I will remember. Essentially, I will be pushing arguments in this order. I actually create some like save functions at the very top of the stack, probably in case something goes wrong, or like even if the fact that do work has to return at some point, so I'm wrapping into some other function. I forgot exactly. So it looks like you exit or something, right? But essentially, so this is your pointer to the work function FNC, right? And then we say, look, everything else like is like EBX, CDI, ASI registers are set to 0, and I'm okay to switch to parent, right? And why do I need to switch to parent when I create a thread? Why do I switch to parent? And someone. From parent to the new thread. Is it? Yeah, from parent to the new thread. But why do I do this? Just to immediately start switching? Yeah, probably. New thread create. That I don't know. Why am I switching to the parent? Can someone guess? Okay, that minor detail aside, and we can debug in assembly in a second. Sure, not clear why I wrote it this way, but more or less, the idea is to create 2 threads. I would say I don't want to run them yet at this point, and really I have to enter this loop and start switching between them. It's kind of like my scheduler, so you can think of this as like I'm picking a dynamically available thread in it rates, and then doing. Make sense? Or okay, now tell me. Okay, if we can write it in the. Okay, let's quickly run and debug. Okay, sure. Like since we. Yeah, go ahead.
They're not done.
Yeah, so yeah, if you're like, for example, in my realistic example, you will have some functions which use, for example, syscalls and say, if I'm sending a network packet, I want to switch to pick a different thread, and I'm entering a blocked state, right? It's a little harder with syscalls because syscalls you really have to invoke them and get stuck in the kernel. So you need some additional support for this. kind of like asynchronous syscalls. So Linux right now has asynchronous, for example, packet submission interfaces. So not everything is asynchronous, but you can say, look, here's the buffer shared with the kernel. You put a request, and then later on you're supposed to come back and check for the completion. So in this case, this scheme works because I put the request, but I don't really enter the kernel. I continue running my user level threads, and then later on, as part of my runtime, I will just go and check again. Right. Let's just quickly try. That's my last change. I don't know, maybe accidentally. Yeah. GDB test. GDB not found. Machines. Where's this? Here's my Linux machine. So. That's a good idea. So the same code compiled on one of the machines in Emulab. GDB test. So layout split. Jesus, that's bad. Is it really this way? Get better lines. Okay, that's better. Yeah. Now maybe because I was running inside the screen. Normal lines, right? Breakpoint on main. Continue. So we got, like, again, for people who don't like GDB, you have the source code, you have your assembly code, right? So I'll start single stepping. So we got we are not sure. So why is that next, right? So in new thread create, where's my GDB? Oh Jesus! So that didn't work apparently. So we'll start it again. Continue here. Everything exited. So we'll start over. Control what? Control L to clear the screen, right? Let's do it again. So this funky function decided not to return, so we'll just do a next instruction. So now we like instruction by instruction, calling this uthread create function. What? I'm in thread 1. How? I didn't say next instruction, step instruction. Jesus. Let's continue again. So start again. Sorry, like didn't do it. Oh, I'm almost there, but yeah, that control doesn't work anymore. So I will do step instruction. Control L. You said okay, control L. So now I'm step instruction really steps assembly instruction. So I will step into this call and we'll be inside uthread create. Let's take a look. Why is that? So like, okay, we're inside the uthread create. So setting all the states, arg, like whatever, initializing everything. But I do, for whatever reason, in my implementation, I decide to switch. Although one would imagine that that's a little odd. Why would you start switching and running the thread immediately? But that's fine. Okay, sure. I don't know why I do it, right? We can comment out this line and see, but the logic is that T1 will start running, and in the first iteration of the loop, switch back to parent, and the parent will return from this, you switch it. That's right. So, but essentially what happens here, if you still step into this, you switch, you're pushing these 2 arguments on the stack, calling you switch, no source code available, but we know the source code of the, like again, is remember stack +4, stack +8 into 2 available registers, EX, CCX, saving Collie, saved registers, saving EBP, saving ESP, restoring EBP from the 2 thread, restoring ESP from the two threads, restoring all the two threads callee registers, do a read, returning to do work function, right? And essentially we are inside the do work function. This is the label here, do work. Right? But essentially that's the very first instruction of the do work function. And essentially, not gonna go into the print and like essentially here we calling a print and here we going call a yield from this. Let's coming back to the yield. Yield sets up the stage for it loads the global variable onto the stack, right? And just calls uSwitch. uSwitch says, okay, I'm ready to switch back to the thread which called me. And here we're returning back this line 72. So we executed one iteration of the thread, right? Agree with this? So not gonna, let's just exit here. Let's just quickly, one would imagine that this line, I don't know, maybe there is some boundary condition which I didn't care to fix, and that's why I put it here, but we can also like say it as well. Yeah, it runs this way as well. So this way I don't switch to the right. Okay, so this is I'll give you this code over so you can read through it. There is nothing magical. We kind of explain it, right? So now a couple of observations, right, which we have to think about. Let's see, let's investigate my own letters to J as part of this history session, which Talia was running. What I wanted to discuss. I wanted to discuss this. This, no, this one, just that, this one. Ah, okay, got it. Actually, we probably don't even need it here. Okay, again, let's step back for a sec, right? I mean, roughly speaking, what this scheme allows me to do is it allows me to capture the state of the running thread as a stack, right? So essentially, like actually, maybe I did it on purpose, and I combine two kind of styles of doing it. So I have a thread data structure, the speed, right? In my case, it has three fields: EBP, ESP, and state. But really, EBP can be on a stack, right? Or I can add more additional fields. I can say, look, my EAX register will be sitting here, or whatever the callee saved registers which I care saving can be part of the data structure. So right now I'm pushing them here on the stack, right? But I don't have to. That's one style. Another style is to how I say in EBP, just push them inside the data structure itself, right? And then restore them from the data structure. Instead of like stack, we can put everything in the data structure, right? What do you think? What is the advantage of it? Why would you sometimes trade stack for a data structure? Okay, it's a little weird question. Maybe it's not even easy to answer, but in my scheme, I kind of allocating the stack for each thread, right? If I, for whatever reason, have a belief that the stacks are so tiny that I don't really have to, like, I don't have to waste all this space for this tiny small computation, and at least the top of my stack is always tiny. If it dynamically grows a lot and then shrinks at the point of yield, then I don't have to waste all this memory, and I can kind of capture everything and put it in a thread data structure. It can be just registers. Maybe it's like you mentioned, maybe it's ADX or or MMX registers, right, or floating point. Like you can say, look, either you can say floating point registers on the stack, or you can save them in memory. It depends, right? So it's kind of like a trade-off. And in a kernel itself, you can say, look, remember we had this question: do you really need a kernel thread for each thread in the system, right? And then the answer is how to construct a system in which you really don't. You allocate one stack. When you context switch, you just make sure that whatever was on the stack, you save it elsewhere. And imagine it's part of your thread data structure or something smaller, right? So this way you say, look, I may be allocating 128 kilobytes to protect against the case where I have an execution which allocates a lot of memory on the stack. But if I have some guarantee that at the point when I yield, for example, maybe I'm finishing the system call in a kernel and I never yield in the kernel itself, but only yield when the system call is over, I know that my step in the state is so minimal that I can save it elsewhere and save those 128K memory, right? So you really can say, look, I can support, like, if I'm shooting for a system which supports like billions of threads, right? It's realistic that this number becomes a bottleneck. And then you say, my state is really like, usually at the point of a context which is much smaller, then just save it elsewhere, right? That's the idea. Make sense? Okay, but it's like next level optimization, right? So the first level problem is essentially how to represent the state. Figure it out. We figured it out. We say, look, we represent the state of a thread as a stack, parent, and two threads which we're running. If we push everything on this stack, then really these two key lines which do this move instructions are the context, the very heart of the context switch. This is where we switch from one thread to another with these two instructions. And before and after, we just restore the state in registers. So of course you say, look, you're probably not running floating point operations in this program. That's correct. If you're using floating point registers, then you do have to save them here and restore them here, right? There are assembly instructions for doing this, right? Same for all other registers. Like if you have AVX registers, you have to save them as well, right? Make sense? But then it's your user level threading runtime.
Is it also a consideration to save in the data structure? For if you, because I'd imagine saving it to the stack could trigger a page call or whatnot. If you want to have, because that thread pretty much owns the stack.
Again, also, can you start over? Trying to save.
So stacks are growing downwards.
Yes.
If by pushing the saving the registers, you cause it to grow when the thread wouldn't actually have needed that much extra space.
You mean like just a little bit to save the registers, like general registers without a take, whatever.
Right. Is that a reason, a similar reason for when to use instead of stack?
To save just because you think that you might run out of space with this 5 multiplied by 8 or something, 5 multiplied by 4.
Yeah.
It's highly unlikely, right?
Okay. So I suppose it doesn't.
Yeah. So really, I mean, even my example, I mean, I don't know what language runtimes are doing and whether they care about how many stacks they support. Most likely language runtimes like async in Rust or whatever the other language, they will allocate a sizable chunk of a stack for each thread and will not care at all. I just wanted to mention it because if we're building this microkernel, we will have a choice. And in microkernel, if you say, look, imagine you never context switch within a syscall and always finish the syscall. Then by the time you finish the syscall and ready to context switch, maybe you even like process the timer interrupt while we were servicing the syscall, and the timer interrupt says, okay, you have to switch. You know it, and you say, okay, I will make a decision. I will pick a victim and switch. But this kernel stack is very, very tiny at this point. So it's literally just 5 things which the interrupt handler puts or syscall. I mean, syscall, since we don't even use the interrupts, It's even like a different convention. It's whatever the registers we put here. So not 5, we say all registers here. So, but it's really a tiny amount of memory. And you say, I don't want to waste the entire 128 kilobyte and just leave them sitting there in a kernel because it's empty, right? And at this point, you say, look, I will save the rest of it. In fact, you don't have to save anything in this example, because if you're done with the syscall, then you really can just say, look, I'm done, just switching. You don't have any state in the kernel, right? So then you can go with one kernel step, right? But that may be too much. But okay, let's just step back and come back to this user level example. So a quick poll. So who understood? I just want to see the level of understanding. 50% of it. Raise your hand if you understood. More than 50. Jesus, wait, like 50. So half of the class or even less understood 50. Okay, people who did not understand, like it's your chance to ask these questions. I can run over it again. Like that's important to understand. That's like when you build computations, you need to understand how to save them and restore them. And operating system does build execution environments for it. What is not even clear how to start asking the question? Okay, I'll give you this code. So suggest you to stare at the code, like single step through it. It should build like any a Linux machine, right? So it's a little hard to build on Mac because of the coding compatibility, but probably possible. Okay, if we understand now for a second how to context switch like this style in the kernel, let's come back to our context switch lecture from last time and think of how can we build a similar mechanism in a kernel, or at least let's just walk through the context switch in x86, right? Let me just and for people who understood like less than 50%, probably a good chance to catch up, because I will explain the same thing, but one more time in the context of the kernel. Imagine for a second, and last time I was explaining the context switch, which was triggered by an interrupt. I should take it back. It's easier to explain when the kernel invokes an explicit yield here, right? Imagine it's not a timer interrupt. Imagine you're running some code, you do a syscall like an IRE, you go into the kernel, right? So on the kernel stack, when you do the syscall with your syscall instruction, right, or sysenter, you start saving stuff on the kernel stack, right? So this kernel stack or syscall stack, if we remember how we built the syscalls, it's available from this like GS relative kernel stack variable, right? So when you landed on the kernel, you started saving the state. Make sense? In x86, it's an interrupt. Then this kernel stack was available from the GDT, right? GDT through TSS. And then inside the TSS, it will be stack pointer 0. So also points here, and the hardware saved. Instead of like using a sysenter syscall instruction, using an int instruction, so alternative right in x86. Then you're here inside like vector 64, which is x86 syscall interrupt. Then you calling into you're pushing a couple of things. You're pushing error code 0. You push the syscall number 64 in the stack. You jump to all traps. All traps essentially start saving all registers, and then calls the trap function by passing this stack as an argument to the trap, right? And this argument is called the trap. Make sense? And so imagine we're inside the call trap. Inside the trap, we start doing some parts of IO. system call, and at some point you say, look, I issued the request, DMA requested the disk, and it's time to yield because it will take us 10 million cycles to come back, right? And so you're invoking a yield function here from inside this call stack. Make sense? In the kernel. You already saved all general registers, like all general registers which user had, user regs, are saved on this stack, right? As part of all traps. So they will be sitting here somewhere. Make sense? Right? And at this point, you say, look, I really only care about this kernel stack. And if my yield, imagine for a sec, we deviate a little bit. You say there's a cron thread and two thread, very similar to how we've seen in the code. Then this yield function can be implemented exactly how we just built it in the user level code, right? Because at this point, it doesn't matter what privilege, like you got it. You remember the fact that you were running in user level. And at some point when you will be iterating, you will be saying, okay, restore this code segment privilege level 3, right? And you will switch to this user level stack, which is sitting somewhere here, for example, which you have like ESP pointer here to this stack, right? But this yield function can be built in a very similar manner to how we build it for my user level library. Does it make sense? Do you agree or disagree? It's cooperative, no timers, nothing, right? You agree? So like this kind of like simplifies the system call, the context switch, because you say, look, I'm taking this user level implementation, right? So which is here, for example, right? Which has this uSwitch function. And instead of like, you will build this uSwitch function here. And as long as you have this convention that you have another computation, if you enter a switch function here in the kernel, like with these two arguments, and you say my 2 points to this stack, and there is enough information so I can there is a return address points to some call stack which is similar to this one. Like again, maybe at some point something was happening, there was all traps, and then there was a trap handler, and there was at some point someone called yield, and yield called switch, right? So you start returning from here, right? And since you know how to return from all traps, at some point you will do an IRAT. IRAT will yield you, like will restore 5 registers, which are code segment, instruction pointer, stack segment, stack pointer, and E flags in 32-bit machines. And you start running back in the user, right? Agree? So this is exactly kind of like how can you build a context switch in your kernel, right? Make sense? Any questions? It's a homework. It will be a homework, so it's better. You better like, but then like you will understand it very well. So hopefully I'll do a write-up for you to explain how it works, right? And now, like, okay, if we understand how the cooperative context switch works, can I ask you a question? What happens on a timer? Imagine we say, look, we want to switch on a timer. How do we change the scheme to support a timer?
Is it, so the timer would be an interrupt, but it's not that the user is calling in. So the interrupt would receive the user program counter and stack, because that's pushed in the trap frame.
Yeah, exactly.
So you could then treat that as a yield, essentially.
Correct, and that's exactly what I wanted to hear. So in x86, interrupt leads into the kernel and results in a cooperative yield. And non-cooperative yield is an interrupt which did not originate in user level, User was just running some random stuff. It's just that when it was running this stuff, the hardware sent an interrupt. It forced you into the same interrupt processing chain. Instead of 64, you will have 32 here, right? But everything else is exactly the same. This will be 32, right? And so you will yield from here and switch to another, and essentially implement the switch in a similar manner. Make sense? Okay. And now, how does it work in Rust? Let me ask you this question. What about safety of Rust?
Nothing of this sounds safe.
I agree with you. This is where the Rust and C are the same, right? Well, yeah, it's kind of like when I was first writing, I was working on the kernel in which I wanted to write as little unsafe code as possible. And I was saying, what about safety, right? And I can still like make sure that all these functions in between this call trap, this is obviously unsafe, this is disassembly. And then between the trap and yield, well, almost everything can be safe. But really, yeah, there is no safety of Rust here. So you break it. So you just have to be very, very careful about what you do here. And obviously you have to say, look, guys, I'm switching between the threads. So if you want to access to any variable from the kernel, you need to do it under a lock, right? And you should be careful to do so in such a manner that you will not trigger a deadlock, meaning that you, like, you know, later on you will try to acquire the same lock again, right? But it's pretty much like C. So all the safety arguments go to hell. So at this point, we are kind of like saying, okay, it's a true unsafe function. So just it can change the execution environment completely, like change any registers, do anything we want. So we have to be very, very careful to make sure that we can come back to this point, return from it, and all the invariants which we assumed before we called this yield still hold after we came back, right? So you have to be careful. Okay, it makes sense. So we understand the Rust, and I'm pretty sure this is what I wanted to explain you. So I want you to build this for me to understand context switch. It's honestly not that hard, especially if you look at this example, you look at the source of x6, you follow the scheme, you get your context switch, right? Something which I wanted to remind you. So this thread create function, obviously you will need to have a similar function in your kernel, meaning that you create a new thread, but you don't start running it immediately. You can, like I just did at user level, but that's probably not what we typically want. But what you need to do is you need to create a stack which is well formed in such a manner that at some point it can IRAT to user level, but before even reaching this IRAT function, it will be like using some low-level exit trampoline, right? To make sure that it can restore when we just leave this stack on the queue of the scheduler. The scheduler at some point picks it up, says, okay, I'm going to yield to it. It restores all the registers, presumably to value 0. It's the very first time you run it. But still, there should be like carefully crafted stack, and this instruction pointer, whatever RAP address which you put here, should be a user entry point, like let's say main or some whatever you choose in the Rust. Let's say Rust main, right? And then this stack, when we yield to it, if it's well formed, will exit to user level, we'll start running this thread, right? So it's also shows you how to when you work on your create thread system call, it has to create this well-formed stack as well. Makes sense? Jesus, I didn't know that you guys will be so. Okay, final question. Who understood 90% of it? Wow, 80%. Well, it's not that bad, you know, like at least a couple, roughly half of the class are above 80 and half maybe around 50, so I assume, but feel free to talk to me. Actually, I promise I will show up for the office hours this week online, or it's only Monday, right? So we still have time. Yeah. Anyway, so that's good. Context switch. So I'm done for today, and we will continue